been here for 2 years now at the University of Toronto as a postdoc. His academic history starts off with the Wuhan Institute of Technology, where he got his undergraduate degree. Then he got a master's degree from the Institute of High Energy Physics, which is the Chinese National Academy of Sciences, right, in Beijing. And then he did his graduate work at the University of Texas, working with Pawan Kumar. And lately he's been doing some work on tidal disruptions that he's going to tell us about today. Thank you.
Thank you, Shen. So yeah, I'm very glad to give a talk here. Okay, my recent interest in tidal disruption events was majorly inspired by recent detection of a candidate event, which I will talk in the later of my talks. And so this work is in collaboration with Chris Messner. And just recently, we started a separate project, which is to analytically and systematically calculate the emission vector of a disruption event. And we have a lead task of Ruby in the collaboration. So to start, we know in the universe there are many active galactic nuclei, and we have a fair amount of evidence suggesting that in the center of each active galaxy, there is a supermassive black hole sitting there and powering the aging activity we see. But how about non-active galaxy? Is there a supermassive black hole in the center of each non-active galaxy? So one possible way to tell about that is to study or detect tidal disruption of a star by a supermassive black hole sitting at the center of the non-active galaxy. So the picture is in the following. When the star wanders from far away to very close to the black hole, then the tidal force from the black hole is going to exceed the self-gravity of the star. Then the star is going to be disrupted. About 1/2 of the stellar material is going to be unbound and ejected away. The other half will be bound, and because there is a spread in the specific binding energy for the binding half, so the bound material will follow different eccentric orbit, and they return back to the original disruption radius. Then they are going the streams of those bound material are going to shock hit each other and circularize. A form of accretion is an accretion that powers a transient flare. So, so the balance between the self-gravity and the tidal force defines a critical radius. So that radius is typically about a few tens of celestial radius for 10 to the 6 solar mass black hole. And there's also a characteristic time scale, which is the return time of the most bound material. And the circularization of the returning material happens on the same order of the fallback time scale. So, as I mentioned, at the disruption site, there is a spread in the specific binding energy for the bounding half of the star. And that distribution of specific binding energy means there is going to be a distribution for the returning time of those bounding material. And also, the mass within the star has a distribution over the specific binding energy. Then the simplest case is to assume that the mass distribution over the specific binding energy is constant, and that will translate to mass rate at which the returning the material, the bound material, returns to the disruption radius and feed the transient accretion disk. So this is a so-called fallback rate, and it has a characteristic parallel, which is proportional to t to the minus factor. So we should, when the tidal disruption event happens, we should look for a flare produced by the transient accretion, and the flare should decay in some similar power house.
Rongfeng, that thing about constant energy conserves, yeah, that one.
Yeah, yeah.
So disregarding the polytrope shape of the star.
That's right.
Partial density distribution.
That's right. And then this is
Beautiful
also,
density.
yeah, this is also connecting the self-gravity system.
Like people have done SPH simulations, right? Did they see some? I mean, did they have enough? Did they see a? Can they get a handle on that exponent, or do they not have enough resolution in some sense, or run for long enough to see?
Yeah, they can get a handle.
And is it close to -5?
It's close. I will talk about that in the later slide.
So there's something right about the assumption.
Yeah,
The-
yeah.
That's surprising.
No, it's not. As you get close to E equals 0, by symmetry, the center of the star will still have DMG. E equals 0,
Right.
or, yeah, it's constant.
For most of
So-
that, it's near equal to 0. Further those at on the side, on the envelope, right?
Actually, most of the material will come from this part. And because when E equals to 0, the fallback, the returning times approach to infinity.
Right.
So which means if you're talking about the rate, then the rate will become very, very small, right? Because, a little bit of spread in the because E is approaching 0, that means T, the fallback time is very large.
Right.
So the spread in the fallback time is kind of very large. Even most of that is concentrated around here, but you have a spread
So this
over
is only
time.
for the early times when the densities, you can see the densities, is that right?
It's for late times.
So
It's for late times. I'm not saying it goes to the minus 5 they're just
Yeah,
late times.
this is
for
a,
sure.
this becoming
Because
more.
that's where you
I'm
can see
surprised it doesn't care about the structure and stuff, but yeah.
You mean less after gas?
No, just the fact that there's more gas in here equal to 0.
Yeah, but the fallback rate for this part will be high because
Sure. Right,
Right.
yeah, I shouldn't be so, I was just surprised that it was,
Why does the E equals 0 marginally on that line go through the center of the star?
because so the E is determined by the location within the star.
it's a paragon of,
Oh, okay.
Yeah. So originally the star is between the bound and unbound.
just something like that.
Okay. Actually, I'm used to circular rules.
So this idea was proposed in 1970s or to the 80s, and later work has considered the internal structure of a star, and they calculate what's the fallback rate profile. It looks like this, and you find the heat-to-mass factor power can be very accurately recovered at later time.
Is that from Mark Reese's paper? Didn't he get the time scale wrong? Did he get 4 3s?
No, it's yeah. This
Oh,
is,
that-
I put it
yeah,
in my hand.
Oh, okay.
So there's a typo there. I corrected it. Yeah, you
It
are.
was typo.
It's not a typo, right? He actually got it wrong.
Really?
Yeah.
But the argument is right.
Yeah, right. Anyway, sorry, I know what you're talking about.
Okay, so one can simply get an idea about the amplitude. So you can estimate the peak fallback rate simply divide one solar mass material that is bound and by this fallback time scale. You find the peak fallback rate is about 2 order of magnitude higher than the Eddington accretion rate, so 10 to 6 solar mass that. So given this fact that the accretion disk formed in tidal disruption event will be have some different characteristics from normal disk. The normal disk, as seen in Beijing or exoplanary, are radiative, efficient, and thin. But the disk in tidal disruption event is super Eddington, so it's relatively inefficient, or we simply call it non-relative, and the disk is thick. It also generates, tends to generate a lot of wind loss from the disk surface. And the main cooling mechanism probably the advection in the radial direction of the disk. So those characteristics of accretion phases has to be taken in mind when we talk about modeling of TDE. So since TDE is a very rare event, so up to now we only have about 15 candidate events detected. Here are a few examples of the TDE vector. So when it comes to modeling of a TDE vector, in the past people just simply use the T2 mass factor fallback parallel to fit the vector, which to me at least has two dangers. First, the vector is more related to the accretion rate history within the disk. So what we know is the fallback rate history, but it doesn't necessarily tell you how the accretion rate should evolve. And second, in order to get the vector from accretion disk, you really need to do the integral of local disk spectrum over the entire disk. And that is the second point is being taken care of by recent colleagues like Linda and collaborators. But again, in those recent modeling work, it is still assumed that the accretion rate tracks the fallback rate history, which we will object at, which we think we disagree with. That will be shown in later slides. And recently, there's this very interesting TDE candidate detected by Swift. The spectrum of this event looks as actually wave band. Here, the red color shows the actual vector, and the time scale of the actual emission work is about a few weeks, and also the radial localization of this event is coincident with the center of the host galaxy. So this information points strongly to the tidal disruption event. And it also turns out that we are not only seeing a tidal disruption event, we are actually seeing the emission from a relativistic jet generated from the accretion disk formed in the tidal disruption event. So this is supported by a fair amount of evidence. And in particular, the radial data of this event is consistent. It can be easily explained by the interaction of this relativistic jet with surrounding media. Okay, for this event, for this kind of jetted TDE event, one has a better chance to model the vector if the emission is really come from the jet. I should mention, the idea is it has a jet, and our line of sight is, we are very lucky that our line of sight is aligned with the jet axis. So that can explain the very extremely high luminosity seen in this event. Because if you can remember, the peak luminosity is about 4 order of magnitude higher than Eddington luminosity for 10 to 6 solar mass black hole. So for the jetted TDE event, one has a better chance to model the vector because if you know the accretion rate history onto the black hole, then you can assume that the accretion rate, the jet luminosity is a very close proxy of the accretion rate onto the black hole. So from the accretion rate history, you can model the vector.
So how can you tell that's from the kind of discussion?
So the radial localization is coincident with the center of the galaxy. So that is consistent with the tidal disruption scenario. And also the time scale is consistent with the fallback time.
Actually, both radio detections off-center, right? Center of EDLA and center of DLBI.
Yeah.
Oh, that's the center. I thought the circle was the center.
So the background is the radio image of the center of the galaxy. So the centroid should be here, right? And the circle.
It's not a big circle, it's a small circle.
Yeah.
The big circle is the SWIFT error circle.
Oh, okay.
Yes.
And that doesn't tell you that it's from the destruction event, right? The diagonal should come from the light cloud, but if the light is coming into play the jet, then you can say that it's a tidal destruction.
And it can be a mini quasar. Sound as well.
I've never seen anything like this before.
The galaxy is a long-active galaxy. So, if you talk about alternative scenario,
Yeah, right.
AGN,
AGN.
yeah, or a supernova.
It's too long last. It has never shown quasar. It looks like quasar, but it's never shown it before, which would be unusual. But I mean, yes, it doesn't mean that it's necessarily a destruction event. It's just not anything else that we thought it was like.
Okay, so in the tidal disruption event, what we know is the fallback rate. So, but I want to know what's the accretion rate should evolve with time. So then the question would be, does the accretion rate is tracking the fallback rate very accurately? So in the past, the answer to this question from people is simply yes. The argument that people have taken is that the accretion time scale or the viscous time scale at the disruption radius is much smaller than the fallback time scale. Then the people think that anytime you through a material around the disruption radius, then that material will quickly accrete to the black hole. But that tells you the fallback rate, accretion rate should equal to the fallback rate. And if you look at, if you think carefully how the accretion can be kept going, it is due to viscous spreading of the material, which means most of the material will go in, but there is a small fraction of material that has to go out to carry away the angular momentum shed by the material that goes in. So this process is a viscous spreading of a ring of mass. So, since the accretion is driven by the viscous spreading, then we should really look at how the accretion rate is determined by the viscous spreading of a disk. So, let's tentatively forget there's a long tail of fallback and concentrate how the a disk will evolve under the influence of viscous spreading. Here, the kinetic viscosity is related to the standard alpha parameter. And the disk evolution due to viscous spreading is in a very self-similar way, in the sense that outer disk radius is going to increase with time in a predictable way. And also the angle, the total angular momentum of the disk is conserved. If the kinetic viscosity is a parallel function of the radius, and if you know the parallel index on the kinetic viscosity dependence on radius, then you can, from those two pieces of information, then you can infer how the viscous spreading accretion rate should evolve. So if that partial index is 1/2, you find the viscous spreading accretion rate should decay at T2 minus 4/3, which is shallower or slower than the fallback rate of decay. For a more general case, if if you don't know the value of the partial index in the viscosity dependent on radius, then you can still infer what's the viscous spreading accretion rate, the temporal parallel. So suppose we have a fallback and it has a long tail. The early fallback will quickly form an accretion disk. Then the fallback rate starts to decay. But the viscous spreading of the early formed disk will have due to the angular momentum conservation, it will have a mass reserve that is hovering around the tidal disruption radius. Then the mass reserve will provide provide a source of late accretion. So the final accretion rate onto the black hole is going to be determined by two terms. One is the viscous spreading accretion rate without considering that there is a long tail of fallback rate. And the other is simply fallback rate, which decays at T2 minus 1/3. So my central point of this talk is the accretion rate onto the black hole is determined by whichever of those two terms that decays slower than the other. And of course, there's a complication factor, which is due to the fact that the disk is going to launch wind loss, and the wind loss is going to affect how the viscous spreading accretion rate should evolve. And this will be addressed momentarily in a later slide. So first, let's study how the viscous spreading accretion evolves without considering the long tail of fallback rate. So one has to look at the evolution of disk accretion regimes. Because since the accretion rate is ever declining with time, so early on maybe the disk is entirely long radiating. And at later times, the disk may have separate regions. The outer disk starts to become radiatively efficient, and the inner disk may still be long radiative. And eventually, the entire disk will become radiative. And this change of accretion phase is important because in each regime, the kinetic viscosity radial dependence parallel index will be different. Then the viscous spreading accretion rate temporal parallel would be slightly different. So after you take into all the accretion phase change, regime change into account, then the outcome will be like this. Here, this is the temporal index for the viscous spreading accretion rate, and this green line is the fallback rate, the temporal parallel. And you find for all three accretion regimes, the viscous spreading accretion rate, temporal parallel, are all slower or shallower than the fallback rate parallel. Once you take into account the wind loss, there will be slight change to the viscous spreading temporal parallel. During the early long radiative phase, the temporal index will become steeper. And in the long intermediate accretion regime, the parallel index can become even shallower. The reason is following. We use a very simple prescription for the wind loss. And we assume the local, the accretion rate within the disk, after taking into account the wind loss, is a simple parallel function of the radius. And S is a free parameter. This is understandable because as the material moves inward within the disk, it loses more and more mass into the wind. So the mass remaining in the disk becomes small and less as it goes inward. So, and we also assume that the region, only the non-radiative region in the disk can launch wind. So during the early entirely non-radiative phase, the entire disk is windy, but the disk is expanding with time. So the final accretion rate onto the black hole is going to be suppressed by the wind loss. Since the wind region is becoming larger and larger, so the suppression factor is becoming larger. So this will steepen the viscous spreading accretion rate decay parallel. But in the intermediate phase, the non-radiative region is shrinking with time, so the wind suppression factor is becoming less and less. So wind loss will shallow the viscous spreading accretion rate temporal parallel. And so here are 4 phases of disk evolution. I'm adding a new phase, which is very early. That earliest phase is defined by the time earlier than the fallback time. So that means during this earliest phase, the fallback rate is increasing with time or above the constant. And after one fallback time, the fallback rate starts to decay. So the later 3 phases are just described in the previous slide. So the final result will be the schematic diagram for the final accretion rate onto the black hole. During phase 0, because the fallback rate either rise or constant, so it's a phase of disk building up. So the accretion rate should be dominated by the fallback rate. So I'm assuming that this is proportional to the fallback rate. Then in phase 1 and phase 2, phase 3, the fallback rate starts to decline, as shown in this green line. And the viscous spreading accretion rate does this. It also depends on the whether there's wind loss or there's strong wind loss. Because the wind suppression factor will be different, and it has an impact on the viscous spreading accretion rate revolution parallel. So if the wind is weak, so then the viscous spreading accretion rate evolution parallel, as shown by this purple line, is always shallower than the fallback rate decay parallel. That means the final accretion rate is always dominated by the viscous spreading accretion rate parallel. But if you have a strong disk wind, then due to the strong wind suppression onto the accretion rate, so the viscous spreading accretion rate does this, as shown in the cyan line. In phase 1, the viscous spreading accretion rate decays even steeper than the fallback rate parallel. So the final accretion rate will be dominated by the fallback rate parallel. But in later phases, the viscous spreading accretion rate is shallower, so the final accretion rate is still dominated by the viscous spreading accretion rate parallel. And we can also analytically calculate the time scales for those phase changes. And the first phase change time is known, it's simply the fallback time scale. And later, those time scales can be also analytically calculated. So now back to this jetted tidal disruption candidate event. Here are the actual lectures of this event. First, you notice there's a strong variability on top of general trend of the vector. If you tentatively ignore those strong Larry variability, you find the general trend is thus that's doing this. It has a more or less stable general trend, and then it transitions to parallel decay. So this general trend more or less resembles our schematic diagram for the accretion rate evolution history. So we can identify that maybe this stable phase corresponds to our phase 0, and this parallel decline phase is corresponding to our phase 1 in the schematic accretion rate diagram. And this transition time scale between stable and parallel decay corresponds to the fallback time, one fallback time scale. Then we can infer the peak fallback rate for this event. And more importantly, our model predicts that the lag curve should transition to a shallower decay at some time, which corresponds to the change between phase 1 and phase 2. So this event is still right. So future observation can tell whether there is a transition or not.
What's the parallel number?
The parallel is between 4/3 or 5/3 or 4/3, because there's huge variability on top of that, so the Phoebe, the parallel index has some uncertainty. So next,
So when you're assuming the initial phase is non-radiative, but my recollection from like SPA simulations is that some fraction of the bound material just goes around in one orbit and slams into and circularizes right away. You have this initial matter sitting there, and I mean, isn't that? I mean, when you have material coming in with matter already being there on one orbit, is it clear that it's going to form? I mean, I realize the accretion rate is low, but is the idea you're just accreting the rest of the stuff that's already there really quickly, and then this is reforming the disk, or?
No, it's not related, not due to, not because the accretion rate is low.
You're saying because it's Eddington, it's called the Eddington rate.
Yeah, super high.
But okay, so but your power law came from assuming. Okay, well I'll have to go back and think about it.
Yeah, you may be because you know, in our galaxy the accretion rate is very low, so that it's radiatively inefficient. That's another extreme radiation.
But the non-rate, how does the viscosity scaling with the viscous kind of scaling in the non-radiative scaling?
So you mean
the power
it's
yeah.
1 half U proportional to radiation.
Okay, so you're assuming it's gas pressure dominated there.
No, it's radiation pressure.
So how do you get U going as R to 1 half?
It's from the energy equation. So the viscosity is balanced by a vacuum for cooling.
Okay, inside.
So I'm neglecting the radiation.
Okay. Well,
What I'm confused about is that when you say T, for T to the minus 5/3 for m dot fallback, that's T since destruction. But when you're talking about T to the minus 4/3 for viscous spreading of the disk, that's T since I laid down my ring that I want to spread, right?
Yeah.
So can't you not just put those on the same power law?
Yeah, we discussed that point.
Yeah, I just don't understand.
Yeah, so I have a slide to show that.
Okay, we can talk about it later.
Yeah, so at the end of the talk, I will show that. Sure. So the disk of precession is interesting in tidal tracking events because in this context, the star's orbit is probably misaligned with the black hole speed if the black hole is a faster spinning black hole. Then the general relativity predicts the frame dragging. It will cause that so-called length theory effect. Simply, the picture is following. If you have a test particle that is misaligned with the black hole spin, then the test particle orbital is going to precess with the period predicted. With the period, it has a strong function of the radius, and of course it also depends on the black hole spin. Because the strong radial dependence of the precession period, then if you have a misaligned disk, then the necessary precession will cause warps in the inner region of the disk. Okay, let's skip this. So then the warp has a tendency to propagate outward through the entire disk. Then what matters is how fast this propagation of warps can be. So in the specific case where the disk is very thick, then the propagation speed of the warp is on the same order of sound speed. Since the disk is thick, then sound speed is high. Then eventually the warp propagation time scale can be smaller than the local precession period anywhere in the disk. So if that's possible, then any warp generated from the inner disk region can be propagated through the entire disk. Then it acts as a transferring of torques due to necessary effect at the inner edge of the disk. So the torque is going to be transferred to the outer region of the disk. So the disk feels the torque as a single body. Then the solid body precession can be possible. So if that's the case, then one can simply calculate the precession period for the solid body precession for the entire disk. It's simply the disk angular momentum divided by the torque due to necessary effect. Then the disk precession period is a function of it's a strong function of outer disk radius, and also it depends on the black hole spin. Because of this strong dependence on the disk outer radius, then if you have a disk that is expanding with time, then the precession period of the disk will increase with time too. We already have a model for the disk expansion. Then we can predict how the disk precession period evolves with time. We find precession period of disk is proportional to time, or even increasing steeper with time. So that's our prediction, if disk precession can be possible. Now, again, back to this jetted TDE candidate. In the X-ray vector, there are many tipping features superimposed on parallel general trains. And if you zoom in individual section of the vector, you find those dips are happening approximately on the same time interval. And if you zoom in a later section of the vector, you find the dips are also happening at some regular time interval. But not all dips are happening at same time interval. So some people have done a systematic search for quasi-periodical signal using Fourier transform technique. They done this search for 4 different sections of the vector, and they find some marginal evidence for quasi-period. So here are 4 quasi-periods from 4 individual sections of the vector. We find the quasi-period is increasing with time. And so the bottom panel is the separation time scale, separation between 2 neighboring dips. You find the separation between the dips are also increasing with time. So here's our idea for what's the possible origin for those dips. Since we are trying to argue that the disk is precess, in a solid body manner. And now for this event, we are actually seeing emission from a jet. Okay, the jet the jet axis is probably associated with the black hole spin, but the disk ejects a lot of wind, and the wind has a strong momentum flux to deflect the jet into a direction that is normal to the disk plane. So under the deflection force of the wind, so the jet is probably forced to always align with the disk normal. So if the disk precesses, then the jet is also going to precess. Then since our line of sight is fixed, then the jet will move in or out of our line of sight periodically. Then we will see the dips in the lag curve. So that's the idea. Then since the data shows that the dipping period is increasing with time, and we also predict that the precession period increases with time. So it's very interesting to compare the evolution of precession period with the dipping period. We find the dipping period increases with time as approximately t to 2/3, which is slightly slower than the evolution of precession period we predicted. And in the bottom panel is the separation time between dips. It's also increased with time, but also slightly slower than what we have predicted. So this slight discrepancy is bothering us a lot, and maybe we are thinking maybe the solid body assumption is not valid. And recently we were thinking another possibility, which is that the wind can carry a slightly a little bit more angular momentum than the material that may remain in the disk. So that if that's the case, then the outer disk radius can be the evolution of outer disk radius can be affected by this effect. So maybe the outer disk radius evolution can be slowed down a little bit, so that the disk precession period can increase with time in a slightly shallower slope. So we are still working on this possibility.
Sorry, can I ask, why do you care about precession time? Because what you're saying is that the propagation of work along this in different radii is short enough that the whole disk is rigid.
It's shorter than the local precession period.
Right. So the whole disk is just rigid.
Yeah, yes.
So while the jet has time variable, the jet is just pointing in one direction as well. So is the disk.
No, I'm assuming that the jet is forced to precess with the disk because of the interaction of the wind. Because the wind is acting as a deflecting.
But the wind is just constant in inertial space, right?
No, the wind is, you can see in average is perpendicular to the disk plane.
Right, which is constant. This
No.
is determined by the outer.
No, since the disk is precess, so the wind direction in average is also precess. Right.
Okay.
Using the direction of the jet is perpendicular to the disk and other obviously the diagram. Using the jet is always perpendicular to the disk.
Yeah.
Around
But you were
Yes.
assuming it's the spin of the black hole.
Yeah, initially I'm assuming that the jet is aligned with the black hole spin, but due to the interaction of the wind, due to the deflection of the wind, so the jet is deflected by the wind.
But this is a rigid body, as you said.
Yeah.
Presumably the orientation is determined by the outermost radii. Outermost radius where any wind will remain, right?
It's a solid body, but it's a precession.
Yeah, there's. Okay.
So the disk plane is not fixed. It's doing like this.
Okay. I see. saying the inner region tries to precess, the outer region just get forced together with it.
The final configuration is the disk will precess as a single, a rigid body. So there's no difference between inner disk
It's
and
what I
outer
don't
disk.
understand. The inner region is very, very elemental compared to the outer body, compared to the outer region. So when the inner region is trying to precess, and if the communication is perfect,
Yeah.
what do you think will happen to like this? I would imagine just sit still rather than try to precess.
No,
It's the precession of the outer disk that's setting the time scale. It's the lens theory precession of the outer disk.
Oh. So
Because
the
it has
outer
radio
one ties down the inner one.
Yeah.
That has a precession. Okay.
Yes, yeah. That's what I mean by fast propagation of words.
Okay.
Are there other places where, like, other than the place, or something where we see, or where we have evidence for processing jets?
Yes, we do. The AGM people observed the geometry and the track of the jet. It shows some helic structure, and that is interpreted as the jet is doing precession. But that's different from this. I'm assuming the disk precesses. So it's the wind forces the jet to precess with the disk. But in the aging scenario, the idea is the black hole is precessing.
There are also some models with QPOs in X-ray binaries that are really precise.
Yes.
I mean, some people think that.
Yeah. So in that case,
Some good friends.
that case is more similar.
Yeah, it's the same exact model.
In the aging case, the black hole's spin precessing period is very slow, so which explains the large helic structure of the jet.
One just real quick comment is that, I think the idea that it's not rigid body is entirely plausible because that all these models that I think we mentioned before assume that the disk is nearly perpendicular to the spin of the black hole, so it's just slightly off alignment. But odds are that since this is a tidal disruption, it could be different by 60 degrees from the plane, and no one's ever done a real calculation of that limit. And it's not clear to me that you can still have a nice, simple bending modes giving you a rigid rotation. I think there's reasons to think it's different.
Yeah, unfortunately.
I mean, I don't know what
find
you
the
I don't know how you
simulation for that. Yeah.
You can get pendulums to do.
Okay, just to mention some other work we are doing. So this is the ongoing work with the visiting student from Tsinghua University for me, and he's now doing a systematically analytical calculation of emission nectar from TDE events. So we are considering when the tidal streams of bound material returns to the tidal disruption radius, then there is going to be strong shock heating, as suggested in Linda's paper. And not only that, since we have a model for the disk evolution, then there's going to be two components of emissions. One component comes from the wind due to shock heating between the tidal debris streams, and later when the accretion rate or the fallback drops to sub-Eddington, then the wind loss from the shock heating will be diminishing, so that the emission will be dominated by the disk emission. So he's calculating the sum of two emission components. And interestingly, if you look at in X-ray wavelengths, the wind emission will have very little contribution to the X-ray band. And it X-ray band will only appear during the later time when the when the wind has diminished. So if this kind of that curve can be observed in an event, then this can give us some idea, whether there is going to be strong wind early on due to the shock heating, and whether our disk evolution model is accurate or not. So we are so the goal is to try to use this disk emission model to some event that has been detected, and try to see we can explain data very well. So here's my conclusion. So one main point of my talk is since the fallback will start to decline as Supermassive chapter, but the early fallback will form a transient disk because of the conservation of angular momentum. Then some material has to be hovering around the viscous spreading, viscous tidal disruption radius, and providing a mass reservoir for the later accretion. So that can become very important in determining the later accretion rate history. And our model has been able to analytically describe how the accretion rate evolved with time across 4 different phases of accretion regime. And we predict that this jetted tidal disruption candidates, that curve will show shallowing transition at some later time. And we think that this precession is promising in tidal disruption events. And this jetted candidates may have shown some signatures, but more work needs to be done to have some firm conclusion. Thank you.
We have time for some questions.
Why does, from the radio emission in that event, why does that seem to peak at later times than the X-ray, or that just the window of observation?
Radio. This is X-ray.
Yes, no, but in the early on, when you showed the SWIFT data and then the radio data of the same event, the radio data seems to be peaking, many months after the.
That actually not the radio data. It's optical data. I haven't shown the radio data.
4.8 gigahertz and give the VLA first upper limit, then you had fluxes at 4.8 and 1.4 gigahertz.
Yeah,
it's very like slide number 3 or so, where you showed the first Swift TDES.
Yeah, I didn't show the.
There was a plot which had a radio flux at 4.8
oh,
and
okay.
4.4
Yeah.
gigahertz.
Sorry.
Yes.
Okay. Yeah, this is the radio data.
Yes, so why does it seem to lag by a large amount?
The idea is that the radio data is not coming from the jet itself, as in X-ray emission. So the radio is coming from when the jet is interacting with the surrounding medium. So that emission can peak at a later time.
But in your picture, we're looking down the jet.
Yeah.
And moving towards the speed of light.
Yes.
That means there's no delay up to 1 over gamma squared, right?
But there is a scalar delay due to the delay approximately r divided by 2 gamma squared c.
Yes, but then you're saying that, how big a gamma are you thinking? Are you going to use?
This gamma is much less than the gamma in GRB jet. It's about 10.
10?
Yeah.
I see. So you're saying that it hits the way the jet comes from stuff, which is, what is it, that's a million seconds? I can't
Yeah, 10 to the 6 a second.
10 to the 6. So that 10 to the 6, when you multiply by 10 squared, so it's 10 to the 8 seconds. So it's 3 light years out that it hits the radio emission. Right.
question?
Yeah, I can answer Linda's question. So, sorry, I have to go to the last slide. So here the dashed line is the fallback, assume the fallback rate profile. So this green line is the viscous spreading accretion rate. For a delta function, so assuming you put some finite mass around one fallback time, around the black hole. So the green line just shows how the accretion rate evolves with time. Okay. So Linda just mentioned that the evolution of this ring of mass will start to will happen on the order of viscous time scale, and that time scale is very small. But if the ring of mass was put at put around the black hole at one fallback time, so we know that the viscous time scale is much smaller than one fallback time, so it will give you a sharp drop due to the shifting of the zero time, right? And now the fallback, you can consider the fallback time history as many superposition of delta function, right? Then each delta function will have its own viscous spreading accretion rate profile. Then if you sum all the viscous spreading accretion rate profile together, then what you get is this blue line. So you find the blue line will asymptotically approach this T2 minus 4/3 parallel, which is the viscous spreading accretion parallel. So
isn't that only fairly late times though? I mean, and it depends on the size of your clip, right? So T fallback is actually, the T viscous is much shorter than T fallback, and you're going to have this big clip, and then it's only going to start to contribute at really late time. I guess I don't know what the different panels are.
Yeah. So this is for a very small viscous time scale compared with the fallback time. Then you see the sharp drop is very significant. So then the T2 mass 4/3 parallel will be reproduced, but at a slightly later time, exactly what you have expected. But generally, the asymptotic T2 minus 4/3 parallel is reproduced.
What is the ratio of T fallback to T viscous in your actual model?
This is a nominal model parameter. I'm assuming that viscous time scale T mu 0 is 10 times smaller than the fallback time scale.
Is that, you've picked an alpha and calculated, you've actually done a ratio, or you?
No, I just assumed this ratio.
Okay.
Just assume.
Maybe one more question.
I guess if in this picture that there's a jet that's coming towards you, the radio emission should show superluminal motion in this geometry with the test points. Did they measure superluminal motion?
No, I haven't heard any claim for that.
Can they?
What is
This is in the northern hemisphere, so they can do it. Well, if we have any more questions, we can ask Rongfeng over cookies. So let's take them again.